Okay, so we continue on with our understanding of the relationship between voltage, current, and resistance. And so what we need to look at here is that we have a linear relationship between current and voltage. In resistive circuits, current and voltage are linearly proportional. Linear means that if one of the quantities is increased or decreased by a certain percentage, the other will increase or decrease by that same percentage, assuming that the resistance is constant in value. For example, if the voltage across the resistor is tripled, the current will triple. If you're not working through these exercises, you're not going to be learning. So it's a good idea to sit down, pull out a piece of paper, and work through these exercises individually, one by one, so that you gain an understanding of what's going on here. So if we show that if a voltage in the circuit is increased to 3 times its present value, the current will also triple. So we need to get used to seeing these diagrams, these little circuit diagrams here. In this case, we've got a battery at 10 volts, we've got a resistor at 4.7 k ohms, and a current flowing through the circuit. So in this case, we know the resistance and we know the voltage in the circuit, and we're going to solve for some current ratings. So with a 10 volt battery, the current then can be solved for by using Ohm's law. I equals the voltage over the resistance. So 10 volts divided by 4.7 k ohms gives us a current of 1.3 milliamps. Okay, so we only have, or 2.3 milliamps. We only have 2.3 milliamps going through this circuit when we have a constant resistance of 4.7 kilo ohms and a constant voltage of 10 volts. So in this case then, we look at what if the voltage is increased by 3 times, 30 volts. The current then will change accordingly. The current will actually triple. So I equals V over R, 30 volts divided by the resistor hasn't changed, it's held constant, 4.7 k ohms, and we get now 6.38 milliamps of current. So you can see the current went up when we increased the voltage, yet we held the resistor at a constant value. So if we look at this relationship now with a graphical representation, okay, you'll notice first off, just first glance look at this thing, it's a nice straight line, hence it being a linear relationship. So if we look at the chart to the side here, where we have 10 volts, 20, 30, 40, 50, 60, all the way up to 100 volts, and we maintain the resistor at 10 ohms, you notice that accordingly the current goes up 1, 2, 3, 4, all the way up to 10 amps. How did we solve this? We just used the relationship. I is equal to V over R, and in this case, a constant 10 ohm resistor. So if we plot this graph, you can do it by pulling out a piece of graph paper and doing it, or you can use Excel and the chart function and chart it out and see that the relationship is a nice, clean, linear relationship. Assume that we are measuring the current in a circuit that operates at 25 volts. The current meter, the ammeter, reads 50 milliamps. Later, you notice that the current has dropped to 40 milliamps. Assuming that the resistance did not change, you must conclude that the voltage source has somehow changed. How much has the voltage changed, and what is its new value? So now if we look at this, the solution says the current has dropped from 50 to 40 milliamps. What is a decrease, which is a decrease of 20%. Since the voltage is linearly proportional to the current, the voltage has decreased by that same percentage that the current did. So taking 20% of 25 volts, or 2/10 times 25, we have a change now of 5 volts in the voltage. So if we subtract this change from the original voltage, we get a new voltage of 25 minus 5, or 20 volts now is present to align with the 40 milliamp current that we are seeing exhibited in the circuit. Notice that you do not need the resistance in this calculation in order to find the new voltage. So it gives you a related problem. You go ahead and try to solve that problem. If the current drops to 0 under the same conditions stated by the example, what is the voltage? Follow the same logic here. Make sure you understand how to solve this type of problem. Looking at inverse relationships then of current and voltage. As you've seen then, current varies inversely with resistance as expressed by Ohm's law. Current is equal to voltage divided by resistance. When the resistance is reduced, the current goes up. That's your inverse relationship. When the resistance is increased, the current goes down. For example, if the source voltage is held constant and the resistance is cut in half, the current will double in value. When the resistance is doubled, the current will be reduced by half. Okay, so you can take a look at how you would graph this to understand the relationship. Okay, so if we look at the graphical relationship here, we've got, again, a 10-volt battery. We've got an ammeter or a current meter in line with the circuit. And in this case, we've got a variable resistor in here. That's what that line through the resistor means. And it says it will vary between 10 ohms and 100 ohms. So in the first column, the resistor is changed from 10 to 100 ohms. And you notice that our current relationship goes down, 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 down from 1 amp to 0.1 amps. Okay, and we do this by using the relationship I is equal to V over R. All right, so in the next section here, 3.2, we're going to look at current calculations when we come back.